and we are going to share the PowerPoint. All right. All right. This is section 5.1. It's the beginning of Calculus 2, or you could say it's the end of Calculus 1. Anti-derivatives. So we've taken derivatives already. If we have a function, once we take the derivative, it looks like this. If I have the derivative and come back to the function, it looks like this. We use a capital F to signify that we had a function derivative and we brought it back to the function. So from function to derivative, and then if we have the derivative, then we bring it back to the function. By the way, this and this are the same. A capital F just signifies that we had a derivative and we integrated it. Antiderivative is the same thing as integration. Okay, so antiderivative is the same thing as integration. Those two words you'll hear, take the antiderivative of it or integrate it, and it's the same thing. So antiderivative is the same thing as integration. So here's the first. I don't know, we already looked at this, but we'll talk about it. If I, by the way, this is the symbol for antiderivative or integration. I don't like to use antiderivative. It's too long to say. Integration. This is the integration symbol. This is telling us to integrate, take the antiderivative. If we have the derivative, once again, and I take the integral of the derivative, my function is a capital F. This just signifies that we integrated a function that was a derivative. So we use the capital F when we had a function already that we that was a derivative and we integrated it. Okay, so once again, this is integration. And this is taking the derivative So if you take the derivative of an integration, derivative and integration, they're opposites of each other. If we have a function and we take the derivative of its integral, you're right back at the function, because derivative and integral, I hate to say cancel each other out, but they kind of do. So they cancel each other out. And I'm going to talk about this C here at the end in a little bit. I'll talk about this C in the end. So the derivative and integration are opposites of each other. Derivative and integration are opposites of each other. Not too bad so far. We're getting there. Slowly but surely. Let's see what the next slide is. Get to it. Okay, so I want to look at this slide first. I want to show you this. I want to look at this, but I want to show you if I have a function that is x squared. What's the derivative of x squared? Anybody? Just want to make sure you guys are awake, or one person's awake. There we go. Thank you. Somebody just chatted the answer. Thank you, Alan. What's wrong? You don't want to talk? The derivative of x squared, you bring the, and I'm going to go through the whole process. I want you to see this process. The derivative is we bring the 2 in front. The exponent is still there. Then we subtract 1. 2 minus 1 is 1. So another way of writing this is just 2x, like Alan said. Okay? Now, if I just took the derivative of a function, if I integrate it, I should end up right back where we started from. This is where we started. So I have a derivative that equals 2x. I need to get back to the original function. When I integrate it, it's going to be the original function. Don't forget, x has a power of 1. Okay, so this is how you integrate. Step 1, add 1 to power of the variable. I'm going to add 1 to that. There was a power of 1 already on x. I'm going to add 1 to it. And so what I end up with is 2x squared. Step 2, take power, put it in front of variable in the denominator spot. Put it in front on the bottom. This 2 that we had, once we add 1, we have a 2. This 2 stays here, but we're also going to take a copy of this 2 and put it in the denominator of this in front of it. Then whatever number is it, whatever constant is in front, we're going to put it in the denominator. And what we end up with is 2 divided by 2 is 1x squared. Do you see? So if we integrate, we just integrated this by adding 1 and then putting that power down on the bottom. When you integrate a derivative, you get the original function back. When you integrate a derivative, you get the, here we go. When you integrate a derivative, you get the original function back, but we label it as a capital F. Do you see? Here's the original function. We took the derivative, and then we integrated it, and we're right back where we began. So the derivative and integration leads us right back where we began. All right, so that's what we're going to be doing. Find the general solution for this problem. And what the general solution, by the way, the general solution means, what does y equal? General solution is y equals, right? We're trying to find y. Here we have y prime, we have the derivative. So we have to find out what y equals. In other words, we have to integrate y prime, because when you integrate y prime, you end up right back to y. The derivative, integration and derivative cancel each other out. So, so this problem here, y prime equals 2, I have to take the integration. Remember, step 1 says add 1 to the power of the variable. Is there a variable with a power?
No.
There is. You just can't see it. Good. I was waiting for somebody to say no. You see how your teacher always sets you up for failure. There is a variable here. What is x to the 0 power?
1.
1. 2 times 1 is 2. Do you see? These two equal the same thing. So to integrate this, you add 1. Step 1 is add 1 to the power. So I have 2 to the 1 power. And then I bring the 1 in, the power down in the denominator. So this integration equals 2x. Integrating y prime equals 2x. So this is my y, or my new, you could call it my new function, or you could say it's my y. By the way, what's the derivative of 2x?
2.
2. Do you see? We're right back where we began. When you integrate it, this is what I get. When I take the derivative, I get 2. I'm right back where I began. Integrating and derivative will cancel each other out. All right, let's move on. Oh, wait, there's more. I'm sorry. There is more. You can tell by there's a little answer down here that's really hard to see. So we said we changed this to, it was this y prime is really 2x to the 0. So we changed y, we added 1, and we divided it by then the 1. We ended up with 2x. However, we have to put a plus c here. In the answer, we have to put this plus constant in there. By the way, c could equal 0, or it can equal, it could equal any other constant I want, 5, 9, -8, or it could equal 0. But we have to put this here because, let me show you the reason why c is here. Why c is here. Why c is here. Why do we add c when we integrate? If I have the function y equals 9, what's the derivative of y equals 9? What's the derivative of 9?
0.
0, right. Now, if I integrate this, if I integrate 0, don't forget x to, if I integrate 0, it's just 0, by the way. If I integrate 0, I need to get back to 9, but I don't know. Do you see? I don't know how to get back to 9 because if you integrate it, there's nothing there. There's nothing there. So it's going to be just a constant. I just want you to see, normally you don't do this. You won't integrate a 0. You can't integrate nothing. But if you integrated it, there's this plus c at the end of it. So we're saying plus c. I don't know what constant it equals. It could equal 9. It could equal 8. Do you see? When we go backwards, we don't know what would equal. That's why we put the c here, because it could be 0. It could be nothing there, but it could be a constant. And when we integrate a constant, when we take the derivative of a constant, it turns to 0. But if you go backwards, we don't know what's there. We don't know what was there before. So we can't put a specific constant down. So we use c. We always, anytime you integrate 0, you're going to put an add c on the end of it. And you'll see when we do a couple of problems here and later on, it comes to play, or we'll find out what that c will equal. All right, so let's try to move on. If I can get to the next slide, there we go. No, wait, is that the same? Okay, here we go. So here's the symbol, here's our function, and we just want to integrate. Okay, so integrate, step 1. By the way, don't forget there's a power of 1 on this x. Step 1 is add 1, so I have 3x squared. Step 2 is take this power and put it in the denominator. And there is a step 3, add c to it. There's the integration. And if you want to, you know, this is my new function. So I'll just say it's my new function. If I take the derivative of this, let's just, I mean, this is the answer, but let's take the derivative of this just to verify. Remember, the derivative of this, derivative, when you take the derivative, you bring the 2 in front. These cancel out, and you subtract 1. 2 minus 1 is 1. And the derivative of a constant is 0. So there's the derivative. We're right back where we began. But there's I mean, 3x is the same thing as 3x plus 0. You see, if I integrate this, if I didn't know if I didn't know what it was when I integrate this, it's going to be a constant because the derivative of 9 is 0. The derivative of 5 is 0. It doesn't matter what the constant is, it's going to be 0. So when I go backwards, I don't know what the number will be, so I have to put a plus c. That's why we always add this plus c at the end after we integrate. Because there could be a 0 there, or it could be a 5, it could be a 9. The derivative of any constant is 0. But for this problem, this is the answer. All right, let's see what else we have. All right, so let's integrate this. Just like when we take derivatives, we're going to rewrite this. We bring this to the top by changing the power of the exponent. So step one is add 1 to the power. Add the number 1 to the power. I'm going to add 1. Step 2, put a copy of the power in the denominator. So what happens is this becomes -3 plus 1 is a -2. I'm going to put a copy of this in the denominator down here. And step 3, add a plus c. So my final answer looks like this: -x to the -2 over 2 plus c. You see this negative, I don't like putting negatives on the bottom of a fraction, so I just bring it to the top. Positive divided by a negative is a negative answer. You can put it to the top, or you can put it, how come it's not erasing? Oh, damn, I'm using the wrong marker, I think. It won't erase. You can put it in the top, or you can put it out here in front. But that's the integration. Add 1 to the power and then put that new power down on the bottom. Yeah, so yeah, I don't know how that happens sometimes. I'm still weird on this. Okay, let's integrate this problem. First, we're going to rewrite it. There's the rewrite. Square root of x is the same thing as x to the 1/2. Add 1 to the power. I end up with 1/2 plus 1 is 3 over 2. Don't put it as a decimal 1.5. So the new power goes to the bottom, 3 over 2, and then we add the c. Now, you cannot have a fraction within a fraction. So you have to understand x to the 3, let's just say x to the 3 over 2 is the same thing as saying x divided by 3 over 2, which is the same thing as saying x times 2 over 3. When you change divide to multiply, you flip the second fraction. So do you see this 2 actually goes to the top, and the 2 goes to the top, and the 3 stays on the bottom. So the final answer would be 2/3 x to the 3 over 2 plus c. You have to understand that when you put this 3/2 on the bottom, the 3 stays at the bottom, the 2 flips up to the top. So that's what the integration of this equals this. And if I take the derivative once again, no, I mean, you can, I would verify all your answers. I would verify all your answers. Take the derivative. You put the derivative is you put the 3/2 in front. You see how everything cancels out, and then you subtract 1. Everything cancels out, and 3/2 minus 1 is 1/2. We're right back where we began. Do you see? You have to understand, you can check your work by taking the derivative. Once you integrate, take the derivative, and you should be right back where you began. Any questions so far? I mean, this first section is real. I think is easy. I promise you, 5.2, 5.3 get harder. It's time consuming. Getting the squares and then using the limit process. Pay very close attention to the videos. In 5.2, there's 5.2, there's theorem 5.2 summation formulas that are going to be really important. So watch that video, that summation formula. See, that's on that test. The show your work part of the test is really hard. Maybe you can do it without the show your work, but the show your work is very difficult in 5.2 and 5.3. Finding the area under a curve, and I'm gonna show you integration here in I'm gonna show you that probably next time, as far as how to do it on a calculator. Integration can be done on a calculator. First of all, let me, before I go to the next slide, I do want to show you if I have a function and then I take the derivative, we know the derivative of a function is finding the slope. We know the derivative of a function is finding the slope. If I have a function and I integrate the function, it looks like an S. It's not an S. It's the integration symbol. If I can try to draw it a little nicer. There we go. If I integrate the function, derivative is finding the slope. Integration is finding the area under a curve. So anytime calculus 1 is finding slopes, finding the derivative, finding slopes at different points. Calculus 2 is finding the area and later on the volume under a curve. Finding volumes of shapes, area of shapes. That's what integration is all about. That's what calculus 2 is all about, finding areas under a curve. You know, what is the area? If you have a curve here, what is this area? How much area is under this curve? We want to know, you know, how many square inches or whatever. What's the area under this curve? That's what calculus 2 or chapter 5 is all about. Finding the area under a curve. All right, next problem. Okay, let's rewrite this. The x comes to the top and it's now a -1. Oh, by the way, don't forget, there's a plus c. When you integrate it at the end, there should be a plus c. I didn't do it on that last problem, but there should be a plus c at the end. I keep on forgetting to put that plus c. So we want to integrate this. First thing, we add 1. What? We get 0. We can't do that. You can't get an x, x to 0. You can't do that. I don't know. But since you can't add 1 to a -1, you get a 0. Let's look. By the way, when you integrate this, it's the same thing as bringing this 3 in front and integrating 1 over x, 3 times 1 over x. On our formula sheet, where's my formula sheet? Look up integration. What did I do with my formula sheets? Oh, I thought I had them. Oh, I must have put them away. Yes, on our calculus formula sheet. Oh, great. We got a new sheet we had to pull up. You have calculus with derivatives, but we're doing calculus with integration. So we're on the side that says calculus integration. If you look at so I'm looking at calculus integration. And so I'm looking, I'm sorry, calculus integration. I want to start off by looking at it says common integrals. Let's look at the first one. So before we move on to this, so I'm just gonna erase this, and we're gonna come back to this in a second. But on calculus integrals, we see this x dx equals, this is a constant. Instead of c, they use k in this paper. It's a constant, and we don't know what the constant is, but it's a constant times x to the 0 power. And in order to integrate this, you have to add 1. So any constant, let's say if you're integrating 5, any constant is you're adding 1 to the 0, and 0 plus 1 is 1, and then you're putting 1 on the bottom. So any constant is a constant times x when you integrate it, plus c. Don't forget about that plus c. So if we were integrating 5, the answer would be 5x plus c, because it's x to the 0, add 1, and then you put the 1 on the bottom. You see, the answer would be 5c. That's the first common integral. Any constant is just the derivative of the integration of 5 is 5x, right? And when we took the derivative of x is 1. Plus c, we don't know what that constant is. The second one on this paper looks like this: xn dx. This is xn dx, and this is 1 over n plus 1 times x to the n plus 1 plus c. This is what we said. We add 1 to the power, and then when we add 1 to the power, we put that new power down in the denominator. So that's what that second one is on this paper under common integrals. All right, so I want you to see the third one. The third one says this: if we integrate x to the -1, it integrates to the natural log of x, right? If you have a function with the natural log of x, the derivative of the natural log of x is 1 over x. So if you integrate the derivative, you're back at the natural log of x. So the integral of x to the -1 is natural log of x, and don't forget the plus c. So this is 3x to the -1, same thing. And if I integrate this, this becomes 3 natural log of x plus c. And they show that the natural log of x is absolute value, but we're going to respect the domain. You can't take the natural log of a negative number. So this derivative equals this. The 3 can be put in front, and the derivative, the integration of 1 over x equals the natural log of x. Just like if I have the function natural log of x, the derivative is 1 over x. And then if I take the derivative of 1 over x, I'm back to the natural log of x. Okay? Uh-oh. Once again, it's just dx. If you don't see a number, there's an invisible 1, just like if you have a number x, it's really, there's a 1x. I don't see a number, so there is a 1 here. And we already said integrating a constant, that first one, integrating a constant, it's the same thing as integrating 1 to x to the 0 dx. You add 1, and then you put this new power 1 on the bottom. So this becomes x to the 1 power divided by 1 plus c. So when you integrate just 1, or if you want to call it nothing, there's an invisible 1 there, or nothing, you end up with x plus c. And the integration of any constant equals x. And I mean, if I had a 5 there, it'd be 5x. If I had a 3 there, it'd be 3x. And then don't forget the plus c. All right, here, this, when we have 2 terms, you can integrate x. My integration symbols confuse people sometimes. and you can integrate 2. So you can do 2 integrations. Don't forget, x is x to the 1. So to integrate this, I have to add 1. I end up with x2, and then you put this new power 2 in the denominator. Integrating a constant changes to x. And then and the 2, don't forget, you can put that 2 over here, and you're integrating 1, which is just x. And then don't forget, at the end of integration, you always put this constant at the end. And if you want to verify it, let's take, this is our integration. This is our new function integration. If you take the derivative of this, bring the 2 in front, the 2's cancel, subtract 1, you get x. The derivative of 2x is 2, and the derivative of any constant is 0. We're right back where we began. How many slides are there today? Oh, no. Please don't make me do this one. So we're going to rewrite this. And we've done this for the derivative, if you remember. This is the same as changing it to x over the square root of x plus 1 over the square root of x. It also means I'm going to change it again to x over x to the 1/2 power. And I'm going to bring this 1/2 to the top. X times x to the negative 1/2 plus, don't forget, this is 1 over x to the 1/2. I'm going to bring that 1/2 to the top, and I get negative 1/2. So and x by itself is x to the 1 power. When you multiply 2 numbers with the same base, you add their powers. 1 minus 1/2 is x to the 1/2. And then I'm going to just separate this and integrate it twice. And this is integrating negative 1/2. So to integrate this now, I mean, we just rewrote the problem. This is the same thing as this. It's the same thing. Now to integrate it, we have to add 1, and I get x to the 3 over 2. And then we put this 3 over 2 down in the denominator. Remember, it's 3, and the 2 flips up to the top. 3 over 2, and you flip it to the top. I showed you that in the previous problem. Here we add 1 to the problem, and I get 1/2. So this is x to the 1/2, and then I put the 1/2 on the bottom. 1, and then the 2, the half part flips up. It flips up to the top, and then you put a plus c. So this actually, the final answer looks like this: 2/3 x to the 3 over 2 plus 2x to the 1/2 plus c. And no, you don't have to change it back to radical form unless the answer was like that. But this is the integration for that. All right. Is this the last one? No, it's not the last one. So if you go back and look at everything we've done, it's really similar to the derivatives. I mean, the problems look really similar. For this problem, you have to use your formula sheet. So I'm looking at my formula sheet, and I'm on the far right side of calculus integrals. I'm looking at the far right side. There's no integration by the quotient rule or anything like that. You have to manipulate this a little bit. And I'm going to show you the manipulation. The only reason why I'm going to show you is because I see it in the book. But let's take a look at what this looks like. What you normally would do with a problem like this is look at your integration formula, sine, cosine squared x. Don't forget, and I just want to stress again, cosine square x is the same thing as cosine x squared. These two mean the same thing. Just want to make sure everybody understands that they mean the same thing. And you need that for the test you're about to take this week. Remember I mentioned something similar to that. So they mean the same thing. So I can rewrite this problem. I have 2 cosine x's. So I can do 1 over cosine x times sine x over cosine x. Do you see I have cosine x squared on the bottom? I have that squared because I have 2 of them multiplying down on the bottom. We know that this equals the tangent of x. Sine over cosine is the tangent of x. Look at your formula sheet if you have the time. I'm looking at it, and I see the different integration formulas. By the way, when you get to calculus 2, if you take it with me, we have an integration sheet with 100 different integrations. 100 different formulas for integrations, because we don't have anything called the product rule or the quotient rule. You have to look through 100 different integrations to find one that will work for you. And I'm looking at this sheet, the far right. I'm looking at the second one down. The second one down has a tangent x in it, but it has a secant. And 1 over cosine does equal secant x. Do you see? 1 over cosine does equal secant x. So on my integration formula sheet, it says integrate secant x, tangent x, and that just changes when you integrate it. It just changes to secant x plus c. So this or this changes to just secant x plus c. The answer to this is secant x plus c. because I used the formula sheet. Integration isn't always that simple. We have 100 different integration formulas. And this can be changed to this, and that can be changed to this. This is on my formula sheet that says change the integration equals this. We're not changing this, where it equals secant x plus c. And that's the answer to this problem. All right, let's look at our formula sheet for e to the x. And I see it in the middle, common intervals. It's 1, 2, 3, 4, 5, 6. The sixth one down, it says e to the x dx equals. Anybody know what the integration of e to the x is without looking at your formula sheet? That's okay. The formula sheet says it equals e to the x, and don't forget the plus c. Because don't forget, if I have this function, the derivative of this function is e to the x. Do you see? It's the same thing. Remember, the derivative of e to the x was e to the x. So the integration of e to the x is also e to the x. So this equals e to the x. And when we integrate, we always add that plus c constant, just in case there's a plus 0 here, some constant that we take the derivative of a constant and it becomes 0. So that's why that c is there. I keep on mentioning that. So the integration of e to the x is e to the x. And hopefully this is the last question. Oh, it is. Good, 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 good. This is the one I always love putting on the tests. A ball is thrown with an upward initial velocity of 64 feet from a height of 80 feet. Find the position function. So I want to start us, before I do this problem, I just want to make sure everybody understands when we start with the position function, we have a position function. I don't know what it is, whatever it is. The derivative of the position function equals the velocity function, right? The derivative of this first one equals the velocity. And then if you take the derivative of the velocity function, you end up with the acceleration function, right? Now, the same thing holds true for integration. If I have the acceleration, see, when you take the derivative, it goes down to velocity, then it goes down to acceleration. But if you integrate, if you start with acceleration, when you integrate, you go up to the velocity function. Then if you integrate again, you go up to the position function. So derivatives, you're going down from distance to velocity to acceleration. When you integrate, you start at acceleration, you go up to velocity, then you go up to distance function. So it says ball thrown upward with an initial velocity of 64 feet per second from a height of 80 feet. Find the position function when the ball hits the ground. Let's start at the very beginning. I don't know anything. I don't know any formula or anything. Oh, wow, this is crazy, but it's doable. Don't forget, I'm gonna start this off again. When we go down, we take the derivative of this, we get velocity. Take the derivative of this, we get acceleration. So derivative, I just want to put it here. We start here and we go down. Integrate, we start here and we go up. So I'm going to write my acceleration function first. So I want to go, by the way, I have to go all the way up to position function. I have to find my position function. That's what we're finding, ST. I'm going to start at acceleration. Can somebody tell me what acceleration is? We've done this already. You should tell me exactly what the acceleration function is. It's one number. We know it. You guys forget everything, don't you? Nobody knows it? Come on. Somebody knows what the acceleration function, what number do I put there? It's something you have to have memorized. And the number is, last chance for somebody to get 1,000,000 bonus points.
I know it's 9.8 if you do it in meters, but I don't know in feet.
Exactly, but we're doing it in feet. It's 32 feet per second square. It's gravity. 9.81 meters per second square is in metric, and acceleration is gravity. Remember, a ball is thrown upward. The only force that's acting on it is gravity. So acceleration is 32 feet per second square. So it's a constant. It's just 32. So to get to velocity, from acceleration to velocity, you have to integrate acceleration. So we're going to integrate the constant. And when we integrate it, we get velocity. Remember in the previous steps that we were just talking about doing, the integration of a constant is just x, right? It's x to the 0 power. You add 1 and put it. So the integration of a constant is just x. So it's 32x. And don't forget about the plus c. Plus c. So this is the velocity function. Now you got to be careful. It says a ball is thrown upward with an initial velocity of 64 feet per second squared. Oh, by the way, this should be a t, right? Because we're talking about time as our variable. This is our time. Our initial velocity is 64 feet per second square. So at time 0, do you see initial? And this is initial velocity. And in physics, the way you write initial velocity is v0. That's at time equals 0. When time is 0, initial velocity, our velocity is 64. Our velocity is 64. So 64 equals 32 times 0 is 0. 0 plus c. So guess what c equals? Do you see? We know c was a constant, but now we know the number. C equals 64. So I can now, here's my original acceleration function. Here's my velocity function now. I can actually write it. My velocity function is 32t plus my c, which is 64. So I'm at velocity. I found this one. I'm there. Now I have to go up to the distance function by integrating one more time. I'm going to integrate my velocity function. Do you see, when you go up, you have to integrate. I'm going to integrate my velocity function. To integrate the velocity function, I'm going to rewrite it, my velocity function, by the way, just so I don't mess up that answer up there. So to rewrite, now to integrate this, don't forget there's a t with power of 1. I have to add 1 to it. By the way, once I integrate velocity, find the position function. Oh, so from here we're going to find the position function. The position function is going to look like this, st. We added 1 to the power of t, and we got t to the second power. And then we put the 2 on the bottom. 32 divided by 2 is 16. The integration of 64, don't forget, is just 64t. It's with 64x, the variable comes into play. And then you have to put a plus c at the end of it. So we started off with the acceleration function. We took the derivative and we plugged in the initial velocity as 64, and we found c is 64. We integrate this, and this is our position function. This is not our answer, though, because I have to plug something in here. It says initially the height is 80. That means if t is 0, 16 times 0 squared plus 64 times 0 plus c. If the position is 80 feet, that's 0 plus 0 plus c. C equals 80. Do you see? So here c equals 80. So I'm going to rewrite now I'm going to write my final answer. My final answer somewhere. I'm going to find room. I'm going to write it right up here. My final answer looks like this. It's the position function equals, down here we have it, 16 t squared plus 64t, and then the constant that we found was 80. That's my position function. So it says find the position function. We found it. It's up here. We had to integrate the acceleration. And then, by the way, acceleration is always 32 feet per second squared. Unless we're using metric, then it's 9.81. So you start off with acceleration, you move up, and we found the position function. Now it says, when does the ball hit the ground? I'm going to leave that up to you. By the way, don't forget, that's when the position function equals 0, when the distance equals 0. You can factor out a 16, and well, let's do it. I might as well do it. That's just algebra, though. I'm gonna do it. I'm gonna erase all this, and I'll do it. Might as well. Might as well. All right. So here's our position function, 16 t squared plus 64 plus 8. When does the ball hit the ground? That means when the distance equals 0. Because right now we're 80 feet above. We want to know when it equals 0. You can factor a 16 out of all of this. T squared plus, oh, by the way, that's a t. I didn't write it in there. 64 divided by 16 is 4. And 80 divided by 16 is 5. Divide both sides by 16, and that 16 just disappears. Factor this. Oh, wait. Something's not right. Did I do something wrong? What did I do wrong? Was there a negative somewhere in this problem that I missed? Because that doesn't factor. Was there a negative? Maybe I didn't want to do it. Oh, there is a negative. How come nobody? Let's go back. I'm sorry. It's going to be really fast. We started off with the acceleration function. It's not 32 feet per second squared. It's a negative 32 feet. Gravity's pushing down, negative 32 feet per second squared. That's acceleration. When we found the velocity function, you integrate this and you get negative 32x plus c, and we ended up with our c being, 64, right? Yeah, 64. So negative 32x plus 64. So there's our acceleration. There's our velocity. And then we did one more, the distance function. You integrate this, we ended up with negative divided by 2, negative 16 x squared plus 64x plus c, which was 80. So instead of x, it should be t's. but this is the function. So this should be a negative in front. I'm just showing you. There's a negative in front because acceleration is gravity pushing down. It's a negative function. So remember, gravity is negative 32. So if that's negative, then I'm going to rewrite this. We're going to, the process is the same. We have a negative in front. 64t plus 80. What I'm going to do is factor out a negative 16. Then I left with a positive t squared minus 4t minus 5. So that's that was a problem because the way I had it is it didn't factor. Now I see it factors. I divide by 16 and the 16 disappears to that 0. And I can factor this now to t minus 5, t plus 1. So t equals a positive 5. And when I it's t minus 5 equals 0, get the 5 to the other side, and I get t equals negative 5. Or t plus 1 equals 0. I get the 1 to the other side, and t equals a negative 1. So there are two answers. Time is negative 1 and time is 5. You can't have a negative time. So when does the ball hit the ground? 5 seconds after it's dropped. 5 seconds later. So it's at 80 feet, 5 seconds later. It's thrown upward with initial velocity, and eventually it'll hit the ground 5 seconds later. All right, so that is 5.1. I'm hitting stop record.